Manuel.
Hi, Emmanuel.
Hi, Emmanuel.
Hello.
Hey, Xiaoming, you are muted. Same mistake as me.
Okay, hi. Yeah, I entered from the public link. Is that right?
That's right. Yes, yes. We first
Okay.
we first listened to the presentation in the public room.
Okay.
We're waiting for Jordan, right? Jordan is not here yet.
I'm here.
Oh, great. Yeah, sorry.
I was making a cup of coffee, so it was incognito.
Great. I think all the committee members are here already. And okay, so Jaren, so maybe we can start. Do you think?
Okay.
Okay. So let me first give a brief introduction to Jaren, and actually thank you everyone for coming to the CC defense of Jaren. And Jaren had, I think, when Jaren first joined our department, she works with Lumin. She works in Lumin's group, and after Lumin left us, she moved to my group. She joined my group, and today she will give a CC defense of thermalization, information scrambling in quantum physics of matter. So for committee members, we will first listen to the presentation of Jaren in this meeting room, and Jaren also sent us the link of another private meeting room. And after the presentation, we will go to the other meeting room to discuss, for the committee to discuss. And everyone else can stay here and chatting and doing some social discussion, etc. Okay, Jaren, if you are ready, you can start.
Okay. You can see the title here right now, right?
Yes.
Okay, great. Thanks everyone for being here with me today. Let me actually get my laser pointer. Okay, great. So in the next hour, I'll be giving my PhD thesis presentation. And the title of my dissertation is Thermalization and Information Scrambling in Phases of Quantum Matter. All right, so my PhD thesis focuses on these three branches of research. So these are nonequilibrium signatures of quantum order. So these basically quantum phase transitions, either symmetry breaking or topological, and how isolated quantum systems thermalize and scramble information from the perspective of quantum simulation with cold atoms. So in other words, quantum antibody dynamics. And I'm interested in the questions of at the overlap of these exciting subfields of quantum antibody physics. So here I distributed my PhD works according to their relevance to these research directions. But due to time limitations, I will be able to focus on just select topics here. And I highlighted these in orange. So the systems I studied in this dissertation are Bose-Einstein condensates, Bose-Hubbard model, Bondi topological superconductors, and spin chains. And many times I utilize exact mappings between some of these systems. Here I list the methods utilized in my dissertation. And I also list at the other side of this circle, I list some of the methods I learned along the way in the collaborations, but not necessarily in the context of my dissertation. Okay. I'll first give an introduction to key concepts in my dissertation, and then briefly review chapters 4, 5, and 6. All right. The concept of equilibration is actually very prevalent in our everyday life, in our macroscopic world. But the question of how it could possibly happen in isolated quantum systems, which are governed by Schrödinger equation, and hence unitary evolution, was actually puzzling for some time. So based on the principles of statistical mechanics, we actually expect an increase in entropy over time as the equilibration happens. That means the equilibrium state is the maximum entropy state. However, the microscopic quantum dynamics of time-independent Hamiltonians are actually time reversal invariant, and the entanglement entropy of pure states remains actually constant all times. This observation already actually suggests that the equilibration of quantum systems is different than the equilibration of the classical systems. So in a measurement, we can write the observable in this decomposed form, where this red square is the eigenstate expectation values, which is governed by the observable that we have, which is all here. And here is the green box, eigenstate occupation numbers, which is governed by the initial state that we use. And then here is E alpha and E beta are the energy eigenvalues. So let me give this notion of this equilibration, like rough notion. Basically, we define it as a dynamical process where a time-dependent observable evolves to some value, some equilibrium value, and remains close to this value for most times during the evolution. So more specifically, average of O of t, time-dependent expectation, basically the time-dependent expectation value. And here, the notation here means the long time average. As t goes to infinity, has to be equal to the value of the long time equilibrium state. And here, again, the long time equilibrium state expectation value here for the operator denoted by this notation. So once this quantum system equilibrates, this implies a form of phase decoherence between many terms here seen. And the superposition of these terms actually gives the time evolved expectation value of the observable. So basically, in other words, the terms in this equation destructively interfere in the long time dynamics, resulting in an equilibrated or what we say dephased state. Sorry. Okay, so this was just some heuristic way of defining equilibration. But the equilibration in quantum systems does not necessarily imply thermalization. For thermalization to occur, typically the long time equilibrium value has to be predicted by a statistical ensemble. For example, here you can see that the observable O, if we're looking at the system operator, system observables, we will be focusing on the microcanonical ensemble. If we were looking at the subsystem thermalization, then we will be looking at canonical ensemble with a temperature assigned. So in other words, equilibrium value must be also the thermal value. There are actually different routes to thermalization in literature, but here I will define eigenstate thermalization, which is studied in the chapter 2 of my dissertation in the context of Bose-Einstein condensates. So the eigenstate thermalization is actually solely defined with the observable O here, observable defined in a time evolution. So formally it goes like this. The eigenstate expectation values is equal to the microcanonical thermal average of O at the mean energy, EM, where we define a narrow energy window like this. So here the microcanonical state could be constructed from the energy eigenstates in the narrow energy window. Here and int is the number of microcanonical, and int is the number of eigenstates that remains in this narrow energy window, and the summation is strictly over these eigenstates that remain in the.
Sorry, so what determines the width of this energy band? So the delta, how are you choosing the delta?
So yeah, that's a good question. So we make sure that the delta is so much less than the mean energy, and practically the way that I choose this is I sweep through like some of the delta values, and I need to make sure that the mean value, so basically the thermal average does not change with delta. So the physics should be independent from the delta.
Yeah, okay.
You choose it. Okay. So the essence of this conjecture is that one eigenstate alone, which will be like any state in the energy window, can encode the equilibrium properties of the Hamiltonian. And these states are called thermal eigenstates. Okay. So the reason why finite size systems exhibit finite size effects is because of the propagation of excitation across the system. When we suddenly quench a system with an initial state in non-equilibrium, what we're actually doing is we're pumping energy into the system, and we create this excitation to high energy levels. So any observable that exhibits quantum revivals actually probe this propagation of these excitations to the edges of the system and the reflection back to the location of the observation. So I give an example here of transfer field Ising model, specifically short-range transfer field Ising model. This is a paradigmatic spin chain, which I will talk about more later. The Hamiltonian has nearest neighbor couplings and a field transfer direction to the coupling. Here, this plot here depicts an equilibrium response of a single site, 1 point observable. And this is specifically the one that we're looking at. We're looking at the middle of the chain in an open chain, and Quench form a polarized state in the Z direction. And here we observe quantum revivals, which scale with the system size. So you can see that the signal decays and then comes back. If I did actually plot the rest of the signal here, we will see some maximum. That will be a quantum revival. And you can see that this actually scales with the system size, which here these curves stand for, running from 24 spins, 30, all the way to 48 spins. Yeah. So since this model is
so this revival time, so you had this energy bandwidth delta, yeah, so in one of the earlier slides. So is this revival time related to the energy bandwidth that matters, or is that?
No, actually, I am right now just giving like a quick like introduction to the key concepts. So I basically just like, I'm just talking about quantum revivals right now. It's not related to equilibration or thermalization at this point. Okay, yes. So since this model is a non-interacting model, we can actually map it to fermions, which I will show later too. And this is the reason why it can be analytically solved. And we have an analytical expression for the maximum quasi-particle velocity as well, which is this VQ here. And as you can see, this VQ, the maximum quasi-particle velocity, can be used to have an estimate of the revival time scale. Okay, a second example is rather an interesting one. The first one was actually a locally connected system with an emergent, like one-dimensional space. The plot here depicts the non-equilibrium response of a spinor Bose-Einstein condensate, which is basically effectively an all-to-all coupled quantum gas. You can see the Hamiltonian here. I won't get into much details here in this talk. However, in this Hamiltonian, we have the annihilation and creation operators for atoms with spins -1, 0, and 1 is a spinor condensate. The first term is the angular momentum operator. The second term is due to the Zeeman field. So after an equilibration, a collapse, in short time, we observe the quantum revivals in the long time. And the finite size scaling analysis reveals that the revival time scale, these times here, diverges with increasing system size. So even though the model is all-to-all coupled with no emergent space dimension really, finite degrees of freedom of a finite size system, finite size quantum gas shows revivals too like this. Okay, so I think one of the most intuitive dynamical behaviors emerging in locally connected quantum many-body systems is the light compounds of information spread. So one of these examples, I guess most famous example, is the Lieb-Robinson bound, the bound that you see here. So this is the natural result of the geometry and the limited connectivity of the underlying lattice. Say like a lattice with only nearest neighbor couplings, like we saw before in the transverse realizing model. So I would say it's rather an extension of speed of light in relativistic quantum mechanics to non-relativistic quantum mechanics, where there is this emergent light cone speed that cannot be exceeded by the excitations of the system. And this is due to the nature of the interactions and the connectivity in the Hamiltonian. So let me first state the Lieb-Robinson theorem here. All this material will give me a better way to introduce the information scrambling. Okay, so given a Hamiltonian with finite range interactions and strictly local observables W and V here, there exists a finite group velocity V called Lieb-Robinson or light cone speed, and this bound here holds where x is the distance between the support of the observables. Here the norm is actually the operator norm. That means we're taking the biggest singular value after doing SVD. And then the A is here, some positive constants, not important for us. Okay, and in this plot, if you want to just match it, X will stand for R actually. Okay, so the essence of the theorem is that there are two things to say. The first one is this operator spread has a finite speed for a Hamiltonian with finite range interactions. So, for example, like for power law decay interactions, meaning that there is a well-defined information light cone that partitions the space-time of excitations into regions like time-like, light-like, and space-like. So what do I mean by operator spread? This is what I mean as in equation, what operator spread, and this is pictorially what I mean. So if you imagine like an initially local operator, in time, this local operator is gonna be coupled to the nearest neighbors, and this is gonna basically the operator is gonna get non-local, more and more non-local. And here you see a linear cone, but this doesn't necessarily the case for different systems. The shape of the light cone could be different in quantum many-body systems. The second thing is that to note about the theorem is the probability of excitation following a space-like trajectory is exponentially suppressed outside of the light cone. So this is basically what we're expecting from a light cone. And the exponential suppression can be seen here in the bound as well. So this plot
sorry.
Yes.
What are the colors in the plot? Because you said we're supposed to see something in it. What do the colors mean?
I will just mention it right now. So this actually plot is a space-time trajectory plot of a transverse field Ising model calculated with fluctuations of equal time 2-point correlators. So those colors are basically these numbers, these values here. These are basically running from t is equal to 0 to some t. Here you can see different t's. And the r here is x. So basically it's the distance, kind of an emergent distance because of the lattice.
So I see an R in the horizontal axis, but I don't see a big R in the thing that you're plotting, which is 2 little r's in it. You said the colors represent the spatial correlator.
Yeah,
but that says an R, little r and R prime, but no big R and no X. So what's the connection between the two?
Thank you for pointing this out to me. Yes. So basically, the big R is the big R is the distance between the spins that I am taking. So I have. Yeah. Okay. Great.
Thanks.
Okay, so what we do here, we determine the contours of very small amplitude, and then we just connect them. This sets the onset of fluctuation growth, that small amplitude here. And the white line is actually that's connecting the connection. And this shows reveals the functional form of the light cone. Okay, and you can see that when we do this, we first see the functional form of the light cone. We can also see we can extract the velocity here, correlation velocity VC, which will be for this model, which is analytically solvable, as I said before, the twice the maximum quasi-particle velocity. And we can numerically extract this and see that it matches with the analytics. Okay, so now building on the Lieb-Robinson bound, information scrambling, let me talk about that. Information scrambling is basically this dynamical process that is complementary to the processes that we have discussed so far. it quantifies the operator spread, which is, we can also say, spread of the correlations across space-time in the non-relativistic quantum many-body system. And it probes the timescales of local operators being non-local. It has an associated timescale, which is called scrambling time. And this is when the initially local operator, like I saw before, showed before in this picture, when it becomes basically the most non-local, given the bounds of the Hilbert space dimension, of course, because we're working with bounded Hilbert spaces here. And this timescale is typically different than the thermalization timescale of the system, which makes it as a different process than the thermalization. And also we can remember that these information scrambling and Lieb-Robinson bounds are basically based on the correlations, while thermalization, as I defined, we were using only one observable. So there are no correlations there. So in other words, scrambling is the process where initially local correlations become lost to the local probes in yet again reversible and unitary quantum evolution. So a natural probe for information scrambling over the operator spread is some form of the commutator between W of t and B. Like this one here, like we saw in the Lieb-Robinson bound, for example. But this turns out to be featureless when we look at this. And the next possible solution is to look at the second moment of the commutator, which is called out-of-time order commutator. And when we have unitary and Hermitian operators, which is the case in this dissertation, we can cast the out-of-time order commutator into out-of-time order correlator. So this is indeed a correlator that is not time ordered. That's why the name is out-of-time order. So these OTOCs were first proposed to understand the information scrambling of black holes. That's where it comes from, quantum gravity. And then it's been explored in great extent in quantum many-body physics. They've been found useful not only in the quantum chaos, detecting quantum chaos, but also when there's no quantum chaos in interacting systems. Typically, it's many-body localization. But information scrambling and OTOCs have also shown to be more broadly useful than just being a probe for quantum chaos and MBL. So in particular, this new branch of research emerged in the field of information scrambling that focuses on the detection of equilibrium and dynamical phase transitions through OTOCs. And this will be the main part of my talk.
Ceren, yes, can you go back to the previous slides? So two small questions. First, can you explain what is MBL?
Oh, sure. So many-body localization.
Okay, great. Yes. So giving the full name is great. So here on this slide, in the first line of equation, you mentioned that this C out-of-time commutator measures the information scramble and how a local operator expand into a non-local operator as a function of time. You also mentioned in the second formula, this F is what you are calculating in most of your study. So can you give a relation between C and F?
Yeah. So this is basically for like Hermitian and unitary operators. This is directly connected. We can basically just extend this. This norm here is the Frobenius norm, and the connection between them is actually direct. It's like let me say like this. So the commutator itself will start growing from 0 to some number that is like determined by the bounds of the Hilbert space. And then when we cast this to the out-of-time order correlator, f of t, it's going to be bounded between -1 and 1. So
I think for many operators, it's just C equals 1 minus F, or F equals 1 minus C, right?
Yeah, so I think it was 1 minus 2 C or something
1
like
minus
that.
yes, right. There's factors. Yeah, great.
Some factor, yes. And for the many-body localization, I won't be actually talking about it in this talk. It's in my thesis, part of one of my works. But I can just say that some systems do show many-body localization. So they show ergodic phase and the many-body localized phase and some transition between it. And many-body localization is basically where thermalization fails. While the ergodic phase, we do see thermalization. Okay. So, all right. So a big chunk of my PhD thesis is composed of studying non-equilibrium signatures of quantum order. So here I sketch a big picture. The left-hand side plot shows a typical phase diagram of a spontaneously symmetric breaking quantum phase transition, with x-axis is the control parameter, y-axis is the order parameter. And the order parameter probes the symmetry broken order in one phase, and it becomes zero in the phase the symmetry is preserved, where these phases are separated by a quantum critical point. So this is the picture at zero temperature. That means it probes the ground state physics. When temperature increases, we observe the crossover originating from the quantum critical point. The question is, how can we dynamically probe the zero temperature quantum order and its phase boundary? So this is interesting from a theoretical point of view, because what we study becomes non-equilibrium quantum matter. But this question is also important for observing the physics of quantum phases and phase transitions in the lab. And due to high control and the precision and the ability to probe real-time physics in quantum simulators, this topic is also ideal to explore in the context of cold atoms. So I will, as I delve into the details of my works in the next slides, I'll try to answer questions here stated. So for example, how can we drive the system non-equilibrium? In this dissertation, this will be exclusively sudden quenches, but there are other ways of driving the system to non-equilibrium. And then which observables should we look at? I'll try to answer this question from a formal point of view, not just with numerical simulations. And then which temporal regime should we look at? And I'll try to answer this question from different perspectives as well, if the time permits. And what is the signature? How to read out how to read out the signature? Okay. So here's a schematic of dynamical detection of quantum phases and phase transitions in quantum systems. A commonly used initial state is a polarized state, as I mentioned before, and I employ this in the dissertation as well. We generally choose an operator of interest, O again, and probe the dynamics of this operator to look for the signatures of this low energy static physics in the dynamics. So we plot that. So a paradigmatic model for this field of research is actually transversal Ising model, but let me say the long range version of it, which includes the short range as a limit. So here's the long range interactions are typically power law decaying interactions, and it has two integrable limits. As I said, one of them is the nearest neighbor local transversal Ising model, which I showed before, and the other limit is the all-to-all coupled limit, all coupled Ising chain. That's actually not a chain. Okay. Yeah. So in most works in the literature, especially based on this long-range transversal Ising models, one focuses on the order parameter operator, like the magnetization average over all sites. This is the case for transversal Ising model. And the dynamical phase transitions of type 1, which is called DPT1, abbreviated as DPT1, is defined when the quench dynamics, after driven to non-equilibrium, equilibrate to some non-zero value in long times. And this long time average of the time-dependent observable could act like a dynamical order parameter, like you see here, demonstrating this phase boundary. And this plot is taken from the reference here. You can see that as system size increases, the profile actually stays, so that what we say order is persistent. This was what's in literature. So now let me talk about our paper. In 2018, an interesting paper actually numerically demonstrated that the OTOC could show dynamical phase transitions and be used to detect ground state quantum phase transitions. So they calculated the long time averages of out-of-time order correlators. And they studied transversal Ising models, both integrable, this one, and a non-integrable cases where I will mention later. And also the all-to-all coupled LMG model. They use ground states or polarized states as the initial states. And they observe figures similar to this. This is a reproduction of their results, where you can see the OTOC average, just a phase boundary. Here the error bars stand for the oscillations of the signal around the mean. So let me note here that the transversal Ising model has a quantum critical point at h is equal to 1, separating two quantum phases, ferromagnetic phase where the Ising symmetry is spontaneously broken, and a paramagnetic phase where the symmetry is preserved. What this work observed, which is the relation between information scrambling and quantum phase transitions, was surprising. Why it was surprising? Let me first note that this is what the type of OTOC that they used was this for this model. It was like at a site, local, single site observables, what we say. So these are not extensive observables like magnetization, as I mentioned in the previous slides, which typically was used in the dynamical phase transition community. And the second thing is their numerics show somehow OTOCs could probe ground state physics too. So remember that these correlators actually probe quantum chaos, which is the property of the entire Hilbert space. So right off the bat, there is no reason to expect actually this happens. OTOCs capture the correlations between matrix elements of observables, whereas the order parameters are typically one-point observables, at least in this model. So we asked the following questions. What are the key ingredients of this connection between a quantum phase transition and an out-of-time order correlators? So why this happens, and how general are these key ingredients? Okay, so to answer these questions, we studied a long time asymptotics of out-of-time order correlators. So imagine I write down the OTOC in terms of eigenstate occupation numbers, which is governed by the initial state, and the eigenstate expectation values, these ones, which is governed by the observable that we use in the OTOC. In the long time limit, OTOC will be 0 unless the energy condition is fulfilled. That means this argument must be 0 to find that energy condition. And this brings 4 energy conditions, as you can see here. The first three ones are the most important. In fact, one can get rid of the fourth one with some assumptions, but for the sake of completeness, I'll keep all of them here. And we see that there's all 4 energy conditions contributes to the OTOC saturation value. And this value can be calculated analytically and compared with the long time average of real-time dynamics as seen in this plot. So the plot is the same plot that I showed you before with real-time dynamics time average. And then I just plot on top of it the saturation value with the red squares, which is this analytical expressions value. So what we propose in this paper is that we propose that this OTOC value is composed of a contribution from the ground state and a contribution from the excited states. And the second part of it, the ground state contribution should be much bigger than the excited states contribution. So if this conjecture holds, then the OTOC long time average should reduce to the ground state contribution. So 2 criteria turn out to be important for the conjecture to hold, one on the initial state and other one on the observable. And this is intuitive. Initial state should be close to the ground state, and the observable fluctuations in its ground state manifold should be suppressed. So when these conditions are actually substituted into the analytical expression that I just showed you, the equation simplifies greatly. In the ordered phase, also due to the nature of the ordered phase, this operator ansatz that we say takes a more specific form, and in the end, the OTOC reduces to a function of order parameter per site. So here, note that the OTOC here susceptible to the degeneracy in the ground state manifold. And in the disordered phase, again, due to the nature of this phase, the ground state contribution is actually suppressed under the high energy levels contribution. However, the criteria that we have here makes sure that the excited state contribution is going to be bounded. And this helps with keeping the OTOC saturation value bounded and small. So then we see basically the clear distinction of OTOC behavior in ordered and disordered phases. Now we can say that the physics of detection is not specific to the Ising model, but rather to like any model that possesses long-range order, including non-integrable models that show criticality as well. So here we plot the ground state contribution on top of others, which are the diamonds one, and it matches mostly and hence explains the origin of how OTOC could probe ground state physics. And we test our theory on a different system here, different system than transversal Ising model. We choose an XXZ chain that hosts two quantum phase transitions between ferromagnetic and XY phases and XY to anti-ferromagnetic phases at JZ is equal to -1 and 1 respectively. And we draw this 2D phase diagram with JZ as in the x-axis and the field is on the y-axis. So this is a phase diagram based on the analytical expression. So the match with analytics is good up to finite size effect. And then we also use our method to mark the phase boundary between XY and anti-ferromagnetic phases, which is basically susceptible to finite size effects. And when we do the finite size scaling, we get like a critical point, dynamical critical point, I guess we should say, close enough to the equilibrium quantum critical point. So let me also say that the method is helpful to see why OTOC saturation value at least cannot capture quasi-long range order. In a quasi-long range order phase, the operator elements of single-site observables are actually featureless, meaning that they're zero. So this means OTOC saturation value actually cannot differentiate between a quasi-long range order and a disordered phases. And here's a plot that actually shows that numerically, that is featureless, and becomes more so with increasing system size. Okay, so the take-home message is that OTOC of single-site observables can actually act like a dynamical order parameter. One of the criteria that emerged from the study was that initial state should be close to the ground state. But could we actually use an infinite temperature OTOC to probe ground state physics too? So this was our second question. The infinite temperature states are more relevant than actual ground states in quantum simulators. And this question is also like theoretically intriguing too, because infinite temperature OTOCs are actually known to probe the entire Hilbert space properties, such as chaos and many-body localization. And it's important to find these counterexamples to the mainstream idea that OTOCs are exclusively quantum chaos and MBL probes, because this is not necessarily true. In the last 2 or 3 years or so, actually more works are coming in to show that OTOCs do not always probe quantum chaos, and information scrambling is actually a broader concept than the quantum chaos itself. So also let me note that one needs to go down to very low temperatures in quantum simulators to probe ground state physics, where like these interesting features reside, for example, topological properties of the ground state. But if OTOCs at infinite temperature could probe the ground state physics, then this restriction will go away greatly. So far, we have dealt with the symmetry breaking order, which has degeneracy in the ground state, and disordered phases, which has actually gapless spectrum in thermodynamic limit. But since we're looking at finite size systems, it looks like the non-degenerate spectrum at finite size. And then based on the intuition that we gained in the previous study, we propose that the connection is possible here at infinite temperature if the spectrum is composed of doubly degenerate energy pairs. And the operator should be chosen to probe these degeneracies. Let me see. Yeah. Okay. So we basically explore this question in this paper here, which is also chapter 5 in the dissertation, and lay out the connection between scrambling and topological order associated with Z2 symmetry. Okay. So an operator that makes this connection possible is a special operator. So the simplest example of the physics can be seen in the transversal Ising model in an open chain, which is dual to a Kitaev chain. So the Kitaev chain is is a 1D topological superconductor with certain parameter ranges, and due to the pairing terms that we have in the Hamiltonian. And then this part, this is the hoping, and then this part, the chemical potential. So edge spin operators can be mapped to Majorana zero modes, and the physics can be analytically solvable for the integrable model, as I said before. And we calculate the OTOC of zero modes, as you can see here. And we specifically look at the infinitely long time limit. And we see that OTOC is governed by the presence or the absence of zero modes. So this is the equation that we derive in terms of the single particle eigenstates and the eigenenergies. And one can see that the equation will be -1 if there is no zero modes. But if there is any zero modes, then the result is going to be different than -1. So clearly differentiating those two cases. And let me note that the system does not have a thermal transition, and the OTOC measurement is done at infinite temperature to probe ground state physics. So I'm just trying to emphasize the contrast there. So the real-time dynamics show a clear difference between topological and trivial phases, as well as the results of the non-equilibrium response of the operators at edge and the bulk. So these two responses here are for the bulk, that they're featureless, and then the rest are for the edge here. Okay. And then the second plot here shows a dynamic phase diagram based on the out-of-time order correlator for integrable transterrestrializing model. So again, for the edge and the bulk observables. This is for the featureless. In the edge, you can see that there is it suggests a clear phase boundary. And we mark the phase boundary at h is equal to 1, very close to h is equal to 1, based on this OTOC of the edge degrees of freedom. Okay, so when integrability is broken without breaking the Z2 symmetry, which means I'm adding this next nearest neighbor coupling terms, the saturation value that encodes the topological order does not survive indefinitely. That means before scrambling fully, the non-integrable system scrambles partially, creating this plateau that we call pre-scrambling plateau, in an analogy to pre-thermalization. So here we observe that the zero modes still restrict the scrambling in non-integrable many-body systems. Here's the long-time data for edge spin operator for near integrable model with a small external field, which still with 15 spins, we can see that the plateau is not a finite size effect. It starts to saturate basically with increasing system size on the same kind of non-equilibrium behavior. So here I won't get into details, but for non-integrable models, since they're not analytically tractable, we utilize again this analytical expression for the OTOC long time saturation value. Of course, we alter it for the infinite temperatures. In this case, in that case, we were looking at the ground state contribution. In this case, we're looking at the contribution coming from diagonal part of the matrix elements. And away from the integrable point, the OTOC saturation value reduces to this diagonal contribution. Here, this plot shows that for different interaction strengths. And the fact that we still have some sort of order profile here with infinite temperature OTOCs and the slow down restricted scrambling in a non-integrable model, which in fact can host quantum chaos, is actually really the evidence of Majorana zero modes. Though of course they're partially localized, right? Because they're interactions and there is non-zero field. But again, even though there's a clear signature of some sort of order here for transverse fields till some value, I'm not going to say critical value, some value, because we don't know whether this one is really a phase transition or a crossover. Anyway, so this possible phase boundary is very off from the equilibrium critical boundary. These systems with these kind of interaction strengths, the quantum critical point actually lies in a bigger age. Why this happens? This is mainly because as we increase the transverse field, the pre-scrambling plateau actually gets shorter and shorter, and eventually with large enough transverse field, the OTOC fully decays rather quickly, or either with no or maybe a very short interval of pre-scrambling. And this caricature here summarizes our results with red markers depicting the OTOC of integrable models and the blue markers depicting the OTOC of non-integrable models. As temperature increases, the dynamic phase boundary shifts to favor disorder in non-integrable models. Okay. Right. I guess I have 20 minutes or so. This should be enough. All right. So far, I focused on out-of-time order correlator of single-site observables. But there are easier quantities to measure in a lab. One such quantity is actually 1-point observable. So now I will explain how quench dynamics of single-site observables could be used to probe quantum phase transitions. Here we work with short-range transverse field Ising model Hamiltonians again, with nearest neighbor coupling, and both integrable. And when there is next nearest neighbor coupling, this becomes non-integrable. So when delta is non-zero. And we apply two complementary methods here. The first one is time-dependent density matrix renormalization group, DMRG. This is applicable to non-integrable chains too, but it's limited to very short times. You can see how short it is from this plot. I will talk about the plot in a bit again. And then the other method, we map the fermionic chain and utilize the cluster theorem. I'll talk about the cluster theorem in a bit too. But this method exact only for integrable model, cannot be used for strongly non-integrable models, can be used for weakly interacting models with mean field theory. We can access much longer times though. Accessible times scale linearly with the system size, and since it's non-interacting, since we're applying to non-interacting models, the system sizes could be actually much bigger. That means if I increase the system size, I can access to more times. Okay, let me see. So, okay, yeah, here we see the non-equilibrium response of strongly non-integrable TFIM with delta is equal to -1. It's strongly non-integrable, and H is equal to 2. Okay, and it's calculated with TDMRG in the middle of a chain with a single site magnetization quench from a polarized state. You see that different system sizes in the legend, and all non-equilibrium response collapses on each other until finite size kick in, and which is shown here with the separation points of each system size. And then you can see the separation points like scale with the system size. So this intermediate temporal regime where all of these curves collapse on each other before the finite size kick in remains in the light cone, meaning that the excitations actually still propagate towards the edges of the chain for that specific finite size system. Okay, so single site 1-point observables in picture maps to a string of fermionic operators in the fermionic picture, which makes the computation actually a lot harder. And the cluster theorem comes as a trick here to calculate the 1-point observables from 2-point observables in times where the correlation between faraway spins in a chain are not built up yet, so they don't see each other yet. In such a temporal regime, this equality holds. The equality is actually exact only in thermodynamic limits. But for finite sizes, as long as large enough, if you take large enough chains, the equality holds effectively exact, numerically pretty good. And the time scale where the cluster theorem breaks down can be estimated with the velocity of the excitations. This is the one that I mentioned before, maximum quasi-particle velocity. This also means that we have a limit to the accessible times, right? But the breakdown time scales with the system size, as I said before. So since each site in a periodic chain experiences identical dynamical response due to this translational symmetry, we can write down the time-dependent single-site observable in this way. And then that means we just need to calculate this 2-point correlator. And we use a Wick's theorem for this and calculate the 2-point correlator in the fermionic picture. In an open chain, though, we use the cluster theorem for spins near the edge of the chain, as this will give a large enough separation between faraway spins. The only difference is that we need to choose spins equal distance from the symmetry center, which is the middle of the chain. And this is because the non-equilibrium response will differ for pairs not equal distance from the center. So we utilize this idea in two papers, chapter 6 and chapter 7. But here I will have time to just briefly mention about the chapter 6. Okay, so we're focusing here for the results for an arbitrary site in a periodic chain or the middle site in an open chain. On the left-hand side figure, you see the non-equilibrium response of a single site when the transverse field is chosen in the ordered phase, meaning h is less than 1. This is an exponential decay, meaning whatever the value of h, the steady state value decays to 0. And we say it has a featureless steady state value in terms of dynamical phase transitions. We cannot use that steady state value to see like dynamical order in the system. That's why we look for signatures in this paper or in this chapter, look for signatures of quantum phase transitions in the transient temporal regimes in periodic chains. So this eliminates, first of all, this eliminates the requirement of reaching steady state regimes, which might be challenging for certain experiments on quantum many-body dynamics, and also explores the potential of single-site observables, which could be probed by recent technologies in cold atoms like quantum gas microscope. The integrable transversal Ising model hosts a crossover at HC is equal to 1, and that separates two dynamical regimes. In a dynamical order regime, single-site observables, as we said, exhibits an exponential decay in time. And in dynamical disordered regime, we observe this oscillatory exponential decay. These distinct behaviors across the quantum critical boundary were actually analytically predicted by Calabrese's paper for late times and thermodynamic limits. And here we will systematically compare our short time results with analytical predictions. Since steady state regimes are featureless for signatures on quantum phase transitions, we focus on the exponential decay rates. These are the exponential decay rates here. So let me first focus on the ordered regime. An observation, the first observation, I guess, although we work with data bounded by light cone, which effectively simulates the results in thermodynamic limits, but in short times, data for small system sizes like 48 spins still experiences finite size effects. We can see this even in the light cone, and you can actually see this in this plot, how it differs from the results for 192 spins. This is because the simulation time is still restricted, right, by system size in the light cone. This is what's so-called the space-time limit. So the black solid line here is the analytical prediction that we calculate based on the procedure given in the Calabrese paper. And this is the equation that we calculated. And that is the black solid line. Okay. So I guess another observation is that, or two methods that I just mentioned for open and closed chains have matching results, which is good. And then why this is important, because open chains are experimentally relevant. And that means we can measure the middle spin in the open chain and reproduce the results for an arbitrary site in a periodic chain. Okay, and let me also talk about this, and then I'll try to finish. Here you see the same plot, but this time in logarithmic scale, focusing on the ordered regime. So another observation, we see this from this plot in the close vicinity of the crossover, even for large systems like 192 spins, we diverge from the analytical prediction. This is pointed by this red arrow here. I will talk about why this is the case. So we propose a logarithmic fit function that can describe the numerical data and is consistent with analytics. This has a seed in power law. And here C0 points to the fact that in a locally connected system, decay rate could never be infinite because of the light cone bounds. And hence, like the C0 actually needs to be a non-zero. So this fit function is consistent with the analytical prediction in the vicinity of the crossover. And this can be seen from the series expansions of the analytical prediction and the logarithmic fit function. This is the series expansion for logarithmic fit function, and then this is the series expansion for the analytical expression that we derived. And the scaling, from matching these two things, we can find that the scaling exponent beta needs to be 1/2. Building on the fit function expression, we define a decay rate function, which is called this one, by exponentiating the decay rates and plotting the decay rate function in the vicinity of the crossover. So this clearly, first of all, this clearly shows this beta half predicted by the analytical expression, which is the solid line, black solid line, and then the green dotted line. But for time numerics, which are the other plots, for system sizes changing from 48 spins all the way to 480 spins clearly show distinct scaling exponents, which is set to beta is equal to 1. So as we move away from the vicinity of the crossover, you can see that the decay rate function at any system size actually converges to the prediction by the analytical expression. So we observe this smooth crossover between different scaling exponent pointed by the red arrow. Okay, if I compare the analytical predictions and the fit function, we observe that fit function always describes the data better in the close vicinity of the crossover. And this is because relaxation time diverges, and one cannot actually reach late time behavior in accessible times for any of the system sizes that we studied at least. So as a result, the analytical expression actually fails for accessible times. And likewise, we observe a scaling exponent of beta 1 instead of beta 1/2. Okay, since I'm running out of time, I'm gonna skip these, but let me just briefly say that here we basically talk about a more experimentally feasible way of measuring this in a quantum simulator. By defining a dynamical order parameter-like quantity, with basically finding the correct scaling so that we rescale the order parameter, and that basically gives us a way to find the scaling law exponent. And these are basically plots for those. And then we also look at what happens to the corrections in the disordered regime in early times, which is really the accessible thing in a lab. I will, and then what happens when we break the integrability. And you can see all these in the dissertation or the papers. These are the notes for those. All right. So in this dissertation, I basically explored the field of quantum many-body dynamics from a range of different perspectives. These are equilibration, thermalization, information scrambling, White-cone bounds, and dynamical criticality, with a variety of systems, Bose-Einstein condensates, spin chains and letters, and fermionic systems. I also looked for answers to the question, what are the signatures of quantum phases and phase transitions in isolated interacting systems driven out of equilibrium? And I found signatures of dynamical detection and determined the paths of how we can extend the quantum phase transitions, both symmetry breaking and topological, to the non-equilibrium setting. So all these theoretical works that I performed and found predictions in this dissertation could be proven in experiments based on quantum simulators. And in this talk, after giving a brief intro to some key concepts, I presented some of the materials in chapters 4, 5, and 6. In particular, we lay down the necessary key ingredients for out-of-time order correlators to probe the ground state physics and the quantum phase transitions. Here, I argued for a universal connection between information scrambling and quantum phase transitions, where when the conditions on the initial state and the observables are satisfied. And then we revealed another interesting connection between information scrambling and the ground state physics, which was basically the OTOC of edge observables are sensitive to the presence or absence of Majorana zero modes, even at infinite temperatures. We marked down a topological phase transition via the steady state temporal regime of OTOCs. And when integrability is broken, we observe this new time scale and the scrambling dynamics of non-integrable and chaotic systems, which we call pre-scrambling. Okay, and then I simplified observable from OTOC at a single site to a one-point observable at a single site, and explain how to utilize the cluster theorem to study the Quench dynamics. In particular, I focused on the periodic chains or the middle of the open chain, where we basically saw that there's a dynamical crossover with associated scaling exponent in the vicinity of the crossover, even in short times. Okay, so based on the talk material, there are a couple of interesting directions. One could study near integrable models with weak integrability breaking. These near integrable models are very useful intermediate models in between integrable and strongly non-integrable models. Such a study would help us to better understand the smoothing of the cuff, which is basically, I skipped that part because of time, but what happens is that sharp crossover in the integrable model becomes a smooth crossover when we break the integrability. And then how our results in chapter 5 about the relation between OTOCs and topological phase transitions can be extended to the fermionic system is an interesting and promising direction of study. And most of this talk was actually on OTOCs, but not on quantum chaos, which demonstrates that the OTOCs probe more than just quantum chaos. So given the conventional ways of detecting quantum chaos is based on energy level statistics, which I didn't mention, but there is still room for finding alternative experimental probes for quantum chaos, and I'm very interested in that direction. All right, I'm sorry, it's I guess an hour now. Let me give my acknowledgements. Okay, I think my advisors, Luming and Kai, for their constant support throughout my PhD. So they always encouraged me in my path to be an independent researcher and provided me a work environment where I could grow. And observing their unique insights of physics along the way was very valuable for my own experience. It was a learning experience for me, and I cannot thank enough for their patience and calm attitudes in their supervision of my PhD. I also thank my committee members for their advice along the way, making the dissertation process smooth for me. Okay, so there are so many brilliant people to thank. I still find Shengtao's and Yong's advices when I started work in Luming's group very helpful. I learned a lot when I was working with them. I had very fruitful exchanges with Tanvi, Yukai, Jenkyu. And in the second part of my PhD, I met Hushu and Xiaowan in Kai's group. I had so many fun and fruitful discussions with Hushu, and I'm looking forward to continue those in the future. Xiaoming was also my academic advisor in PhD, and her advice for my academic success, especially in the beginning of my PhD, was very helpful. And in the last year or so, I had this opportunity to take a part in the study group of Xiaoming and Kai, where I learned so much about topological mechanics and in general, the role of topology in physics. In the study group, I had very fruitful exchanges with Francesco. I learned so much studying differential geometry in thermodynamic spaces and information geometry, which was part of the MQ Foundations of Thermodynamics and Statistical Physics project. This was an opportunity provided to me by Christine and Gabrielle. I actually started to learn information geometry with Yoon in Department of Math and Psychology in my first year. Information geometry didn't take a part in my thesis, but it was very formative throughout my PhD, and I hope to make use of it in the future. I took my quantum field theory courses with Finn, and I still remember, I don't know if Finn is here, but I still remember that it was during his second QFD course when I had to decide what to do with my PhD after Luming left the country. If I didn't enjoy RG so much, I would probably not dare working with Kai at all. So Finn encouraged me a lot, so many times in the beginning of my PhD to work with Kai and gave me so many helpful advice along the way, both about academia and research, and I cannot thank him enough. I spent so much time in MagLab, Florida, and learned so much from Paul and Oscar, talking about different condensed matter topics. I guess it was them talking about twisted bilar graphene all the time was the reason why I found myself in that field after all. Thank you very much. Yes, and Özgür was my undergraduate advisor and my collaborator during my PhD. My interest in non-equilibrium physics is heavily affected by him too. And in Özgür's group, I met brilliant people who touched my academic life in some way or another. In the last year of my PhD, I had a great opportunity to collaborate with Jad and Philip from Hoke Lab at Toronto. And I'm very happy that our work actually turned into the last chapter of my dissertation. I also thank Amos for teaching me a lot about random circuit theory in our current collaboration. I guess last but not least, none would happen without the constant support of my friends. And my family back in Istanbul. I thank them so much for their support when I'm away. Seeing them proud makes me proud too. And in the middle of a pandemic, job search, and thesis preparation, I also got married. I guess there's nothing like sharing my passion for physics with my partner for life. I'm so lucky to have you, Paul, and Aslan or Kat by my side. Thank you very much for listening to me.
Yeah, it's a great talk. Yes. So let's first ask the general audience. So from so any questions from the general audience, and a committee member can will ask questions slightly later. Okay. Any questions from the audience? Okay. So so for the committee member, we will move to another private discussion room for more questions. But if any committee member has actually questions want to raise in front of general audience, please you can do so right now.
Ceren, I have a question for. So initially you have shown that this recurrence time, quantum recurrence time, which go up with linearly with the system size. I also noticed that for some system, which probably go up exponentially with the system size. Is that a special property of your Hamiltonian model, or is that something which
different? You mean
the recurrence time, quantum recurrence times? I showed that something at the beginning that I guess for your model it goes up linearly with the system size, like this one.
Yes. It was linear, yeah.
And also the previous page, it also goes up linearly, right? It's a recurrence time goes up with linear right. With the system size. Is that a special property of this Hamiltonian? Because I know some model it might go up exponentially, right?
So this is the case, I think, for this Hamiltonian, because Hamiltonian is analytically solvable, and the way to think about it is really like we have a chain, and then we have this quasi-particle velocity for the excitations to go like reflect back and come back. But for different systems, we don't have an analytical, like for non-integrable model, for example, we don't have an analytical expression for this. So I cannot exactly say whether it's going to be proportional, like it will be linear in N or not. That's a good question. I'm not sure. One needs to, I guess, do numerical simulations for that.
Okay. So another question is for this you show a model where with the next nearest neighbor interaction, where you show there's a pre-scrambling and there's scrambling behavior. Is that also is that behavior, is that generic? So if I have a different Hamiltonian or different model, do you expect there will be also a phase of this pre-scrambling phase?
Yeah. So the we tried this with different models, like still Eisen-like model, the XXZ model, for example. We were seeing the pre-scrambling, though in those cases, since XXZ model is integrable model, the pre-scrambling time is expected to actually indefinitely continue last. If you look at a different non-integrable model with different type of system, non-Ising system, I'm not sure how that will work out with the, that's basically something that I'm interested currently, that I want to see, especially in 2 dimensions. But yeah, so this is not like just valid for transterrestrial Ising model. It happens in other spin chains as well.
So yeah, so in principle, this should work for any model that has Majorana 0 mode until the end of the chain or until the boundary. But so far, you know, because the Majorana chain model can always be 1D chain model can always be mapped to Ising model. So far, all the model we studied are Ising.
Yeah.
Okay.
But the fundamental physics is actually Majorana zero mode. As long as the system gives Majorana zero mode, in principle, it should be there.
Okay.
Oh, and also about the revival time, I think Lumi is asking actually a very important question. So what is governing the revival time in this model? For this specific model, I think, and this to my understanding, this particular time Ceren observed in the simulation is roughly the time where the signal goes through the boundary and then get bounced back to the point where Ceren is doing the measurement. So that's the reason why it scales linearly with system size. Or for periodic bounding condition, it's the time that the signal cost takes to go around the system and come back to the original point.
Yeah, that's basically because it's just 1D chain. Or how that will happen actually if we have a two-dimensional system or even a ledger system. One needs to think about those, like how those reflections will probably also like superpose, and it's not really straightforward to say, well, like the type of scaling there.
Yeah. And under these systems, I think low energy physics has Lorentz symmetry, if emergent Lorentz symmetry. So there is a well-defined light cone and well-defined velocity. So one can really get the velocity, how long it takes for the signal to go to the boundary and bounce back. That's pretty much the same time scale Ceren observed here.
Because I remember for some random, probably some random Hamiltonian or some random circuit model, the quantum recurrence time, there's a theorem which proves that the quantum recurrence time is exponential in system size.
Right.
So
I think in general it should be exponential. Yes. Yeah, I agree. Yeah. So here I think one difference is that I think in general for quantum circuit model, it has this long range all-to-all interaction, and there is no spatial information propagation and the bouncing back this procedure in general. But here, I think the signal here is dominated by the signal go to the boundary and then bounce back, and this minimum. Okay, great. So I think if there's no questions from the audience or questions for the audience, Ceren and the committee, we will move to another discussion room, and everyone else can enjoy your chatting and your chatting here. And so if you do you guys all have the other link for the other room? If you do, let's move there. Okay, great. So if you need the link, let me know. If any committee member need the link, let me know.
I don't have the link. Where the link?
Okay, I can send you the link. Just 1 minute. Let me see. Where it is. Give me 1 minute. Oh, here. Okay. Chat. Okay. So Lumi, I send the link to you through chat.
It's an email or it's a where?
It's a Zoom chat.
A Zoom chat.
Right. I think near bottom part of the screen you should see a chat button. Oh yeah.
Okay.
Okay. Yes.
I am leaving.
Okay. I think all the committee members are there. So okay, let's go to the other room.